Hi students, let's discuss today about the effect of boiler pressure, condenser pressure and superheating on the simple Rankine cycle. First one is effect of increasing boiler pressure in Rankine cycle. Now let's discuss about the effects. For discussion, let me draw the temperature entropy diagram. This is temperature entropy diagram. So this is the vapor dome, saturated liquid line, this is saturated vapor line. Now let us assume the steam at the turbine inlet is at state 1 here. So 1 to 2 it undergoes isentropic expansion. So 2 to 3 undergoes condensation, 3 to 4 pumping, so 4 to 1 this is saturation. So this is the cycle 1, 2, 3, 4. This is how we represent the Rankine cycle on the TS diagram. So this is happening at a boiler pressure P1. This is the condenser pressure. This is the condenser pressure line. This is the condenser pressure line. Okay, pressure condenser constant. Now as we are discussing effect of increasing the boiler pressure, so boiler pressure, this is the boiler pressure P1. Before that, this is the heat input Q1 in this cycle, this is the heat output, that is heat rejected is Q2 in this cycle. I will represent the cycle 1, 2, 3, 4, 1 as Rankine cycle with pressure P1. I will call this cycle as low pressure cycle. Here let me write the area of heat rejection, because I will be taking for my discussion as well as comparison with high pressure cycle. So I will take this as X point and this as Y point. Now the area 2xy32, that is this area represents heat rejected in this cycle as per basic thermodynamics. That is area xy32x is equal to Q2 with P1, that is heat rejection with boiler pressure P1. Now this is the area enclosed within this cycle. This area represents network developed in this Rankine cycle. Now as per our discussion, boiler pressure has to be increased. I will increase now the pressure, boiler pressure to P1 dash. That is, when I increase the pressure line goes up. This is the pressure line, new pressure line, but I maintain the same saturation temperature. This is the point 1 dash. This is our new point 2 dash, and here I'll get x dash. So then 2 dash to 3 is condensation, 3 to 4 is pumping, so 4 to, this is the new saturation line, this is the new pressure line P1 dash, but P1 dash is greater than P1. Now the new cycle is high pressure cycle, that is, which is the cycle? 1 dash, 2 dash, 3, 4, 1 dash is the high boiler pressure cycle, Rankine cycle. For the new cycle, if you observe, what is the heat rejection area? Area for the heat rejection is x dash y 3 2 dash x dash, means only this much area is the Q2 with P1 dash. So now finally, as per our discussion, this is the area which makes the difference. This represents heat reduction in the heat rejection. Reduction in the heat rejection. What this represents? Reduction in heat rejection. This is saved due to increase in boiler pressure. Friends, we are discussing the effect on thermal efficiency, means we are saving the heat rejection. Heat rejection is saved here. We know that thermal efficiency is given by net work upon heat supplied. Net work can also be written as heat supplied minus heat rejected upon heat supplied. Here, as we have saved the heat rejection, means this quantity got decreased, means numerator value increased. So hence, if heat rejection is decreased, what about the thermal efficiency? Numerator value will increase. So because of that, thermal efficiency is increased. Hence, by increasing the boiler pressure, we are able to increase the thermal efficiency of the Rankine cycle. So the net effect because of increase in the boiler pressure is there is an increase in the thermal efficiency. Now, what about the net work developed? Here, from first cycle, lower pressure cycle to higher pressure cycle, this is the net work decreased, but the same area is increased here. So there is no much difference in the net work developed. So this was all about the effect of increasing the boiler pressure. Friends, let's go for second point, that is effect of condenser pressure. Effect of condenser pressure. Effect of decreasing condenser pressure. For understanding this also, let me draw temperature entropy diagram. This is temperature, this is entropy diagram. So this is our vapor dome, saturated liquid line and saturated vapor line. So now let me draw first simple saturation cycle. So this is the saturation cycle. This is 1 2 3 4. This is the simple saturation cycle that we draw. Means this is the cycle. Now here this is the boiler pressure P1, this is the condenser pressure, this is the condenser pressure P2. Now we are discussing about decreasing the condenser pressure. Decreasing the condenser pressure. Now here the area enclosed by this complete cycle is the network developed. Area enclosed by this complete cycle is the network. So here the network with P1 W net when pressure is P2, sorry, condenser pressure is P2. Network developed is area enclosed by 1 2 3 4 1 on this TS diagram. Okay. So now let me decrease this condenser pressure P2 to P2 dash. So I will decrease it. When I decrease the condenser pressure, so this is the decrease new pressure line, that is 2 gets shifted to 2 dash, 2 gets shifted to 2 dash. So this is the new pressure line, that is P2 dash, new condenser pressure line, decreased pressure line. So 2 gets shifted to 2 dash. So similarly 3 gets shifted to 3 dash. So 3 dash to 4 we will pump it again, 3 dash to 4 dash, 3 dash to 4 dash. This is 4, this is 4 dash. On this graph, this is the decrease in boiler pressure, that is condenser pressure. P2 dash is less than P2. Decrease in the condenser pressure. So because of that, what we observed, now what is the new network developed in the new cycle? W net with P2 dash is area 1 2 dash 1 2 dash 3 dash 4 dash 1 is the new area, this complete area. Now which one is larger in this? This area is larger than this area. That is, by decreasing the condenser, means we also know from the basic thermodynamics. Okay, so as this area is bigger, the network with P2 dash, that is decreased condenser pressure, is larger than the network with only P2. Therefore, what we write? Network with decreased condenser pressure is larger than the network with the condenser pressure P2. Therefore, network is increased when condenser pressure is decreased from P2 to P2 dash. This is the first effect. We also know that thermal efficiency is equal to W net upon heat supplied. So heat supplied for both cycles is same, that is H1 minus HF4 is same for both the cycles. But as W net is increased, thermal efficiency also increases. So therefore thermal efficiency is increased due to decrease in the condenser pressure. So this is the second parameter. Now let us come for discussion on the third parameter, that is effect of superheating. Effect of increase in superheating. So if I increase the superheating or degree of superheat in the Rankine cycle, what is the effect? Let me draw temperature entropy diagram. So this is the vapor dome that we draw, saturated liquid line, saturated vapor line. Now first let me draw the simple saturation cycle. This is saturation temperature at the boiler. So this is the pressure line. This is the pressure line. First let me indicate state 1 here. 1 to 2 is isentropic process. 2 to 3, 3 to 4, 4 to 1 again. This is 3, this is 4. Now here this is the simple saturation Rankine cycle. Now the degree of superheat is till state 1 only. So this is superheat temperature, T superheat 1. Now what we need to observe? The effect of superheating. Effect of superheating we need to observe. So here if I increase the degree of superheat or superheat temperature from 1 to 1 dash, what is the effect we have to observe? First of all, the network without increase in the superheat is, what is the network now? The area enclosed between 1, 2, 3, 4, 1. This is the area. Okay. So this is the area which gives network before increase in the superheat. Now if I increase superheat temperature from 1 to 1 dash keeping the same pressure, so 1 to 1 dash, so I am increasing the superheat temperature. See, there is an increase in the superheat temperature. This is T superheat 1, this is T superheat 1 dash. So this is T1, this is T1 dash. Superheat, increase in the superheat. If I increase this process, there is a, then what happens? 1 dash to 2 dash, that is isentropic expansion happens in the steam turbine. So this is the 2 dash. This is the condenser pressure line. So 1 dash to 2 dash is the new. Now if you observe, because of increase in superheating, there is a increase of this much net work. So this is the increase in network. Increase in network because this much area is increased, 1 dash, 2 dash, 2. So this is the increase in the area. Parallelly, there is an increase of heat input also. 1 to 1 dash it is increased. So this much heat input also increases. There is an increase in network as well as increase in heat input. So as W net is increased and network is increased, so we know that the thermal efficiency is W net upon heat supplied. So network also increased, heat supply also increased, but the overall effect is there is an increase in thermal efficiency. So therefore thermal efficiency is increased. Thermal efficiency is increased. So friends, one more effect of superheating is, if you superheat the steam, how about the quality of the steam, that is dryness fraction of the steam in the state 2. Earlier during the process 1 to 2, the state 2, that is state 2, its dryness fraction was x2. Now after superheating, the dryness fraction is x2 dash. So if you observe, x2 dash is tending to the value x equal to 1, that is the dryness fraction is increasing, that is x2 dash is greater than x2, means more dry steam leaves the steam turbine. That is a additional benefit of superheating. So if wet steam is formed inside the steam turbine, it creates erosion of steam blades. So it is a one more benefit for us. Friends, these are the effects. Now let us discuss about actual vapor power cycle. Actual vapor power cycle. Okay. So you know the difference between ideal cycle and actual cycle. Always actual cycles includes actual processes with frictional losses, heat losses and other losses. So because of that, the process behavior always changes. First, let me draw TS diagram for better understanding. See here, this is the temperature entropy diagram. This is the temperature entropy diagram, that is temperature entropy diagram, vapor dome. For ideal cycle, you know how to represent the, this is saturation temperature for the boiler, this is superheating, this is expansion inside the turbine. Now this is the cycle, ideal cycle 1, 2, 3. Everybody knows how to represent this cycle. Now 1 to 2 is turbine expansion, 2 to 3 is condensation, 3 to 4 is pump. Here we are sending pump work inside. So here we are developing turbine work. Then again 4 to 1 we are adding heat, that is Q1 we are writing, 2 to 3 we are rejecting Q2 heat. So this is the ideal cycle, ideal Rankine cycle. Now how actual means, there are 4 devices, 1 to 2 is turbine, 2 to 3 is condenser, 3 to 4 is pump, 4 to 1 is boiler. So all these 4 devices functions for 100% efficiency in ideal Rankine cycle. But actual conditions, practical situations deviates from ideal conditions because of losses, frictional losses, heat losses and other losses happening inside the devices. So because of those deviations, the behavior of the process changes. Now the same processes deviates, how they deviates. So this is the condenser pressure line. Now 1 to 2, it is isentropic process, that is ideal process. Actual process deviates like this. This is 2 dash. Because of what? Deviation is because of losses. So 2 dash we mark here because of losses. So now 1 to 2 dash. So 2 dash to 3. Now because of losses in the condenser, 2 dash to 3. So this is the process. So 3 to 4 dash. 3 to 4 dash. This is the 3 to 4 dash, that because of losses happening inside the pump. Earlier it was isentropic pumping, now it is deviating 3 to 4 dash pumping process. Now 4 dash to, again liquid remains same, now 1. So because of this there is a deviation. This is the state 1. So this dotted line represents the actual cycle, actual Rankine cycle, and continuous line cycle represents ideal cycle. So this is about the Rankine cycle. Students, for better understanding, we ignore the losses happening in the condenser as well as boiler, and we take the losses into consideration for the turbine process as well as pumping process, because these are the machines have many rotating parts, more losses are there. So due to that reason we consider turbine losses and pump losses. Because of that we define efficiency for the turbine as well as efficiency for the pump, and we represent the same process by considering only turbine losses and pump losses. We redraw the cycle in this way. So that is 1, 2, 3, 4 is the ideal cycle. Now because of deviations I mark this point 2 dash here, ignoring the losses in the condensation process. Then 3 to 4 dash I mark here. So considering only turbine losses as well as pump losses. This is turbine, this is for pump. I ignore losses in boiler also. So this is the TS diagram that we follow while solving the problems. So because of these deviations in turbine as well as pump, we need to write the formula for turbine efficiency as well as pump efficiency. Before writing the formula, let me draw enthalpy entropy diagram for the actual cycle. Enthalpy entropy diagram for the actual cycle. See here, this is the enthalpy plotted on y-axis, entropy plotted on x-axis. This is entropy. For this process, this is the vapor dome. This is a saturated liquid line, this is saturated vapor line. Now here we have a condenser pressure line, this is the boiler pressure line. So now our steam is in superheated vapor condition. This is superheated vapor zone. Here liquid plus vapor zone, this is completely liquid. So state 1 we are marking at the inlet of the turbine, state 1. So state 1 to 2 it is undergoing. This is S1 is equal to S2, ideal process inside the turbine. So because of losses there is a deviation, that is increase in entropy and enthalpy. The new process is H2 dash. See here, this is about the enthalpy. This 1 to 2 is ideal process, 1 to 2 dash is actual process inside the turbine. So I write turbine efficiency formula considering this process, these two process. So how do we write? Which one is smaller here? 1 to 2 dash is smaller, that is H1 minus H2 dash is smaller, H1 minus H2 is larger. This is ideal enthalpy change, this is actual enthalpy change. So turbine efficiency, I define it as actual enthalpy change divided by ideal enthalpy change, that is turbine efficiency is equal to H1 minus H2 dash divided by H1 minus H2. So how do we write the turbine efficiency? Turbine efficiency formula I will write here only. Turbine efficiency formula is equal to H1 minus H2 dash divided by H1 minus H2. So this is the turbine efficiency formula. So now coming to pump, so 2 to 3 there is a condensation, 2 to 3 there is a condensation, 3 to 4 this is ideal pumping process, and 3 to 4 dash because of deviation, that is actual pumping process. Now H3 minus H4 dash is actual enthalpy change in the pump, and HF3 minus HF4 is ideal enthalpy change inside the pump. So 4 dash is here, I should not mark this, this is wrong, this is 4 dash. H4, now this is the pump efficiency formula. So pump efficiency I will write, which one is greater here? Greater is 3 to 4 dash is greater, because of losses it will consume more work. So because of ideal conditions it will consume less work, 3 is lesser. So how do we define the pump efficiency? HF4 minus HF3 divided by HF4 dash minus HF3, that is, how do we write the pump efficiency formula? So I will write here, I have the space. How do we write pump efficiency formula? I am writing pump efficiency is equal to smaller is HF4 minus HF3 divided by HF4 dash minus HF3. Okay, HF4 dash minus HF3. The same formula can also be written as H4 minus H3 divided by H4 dash minus H3. But finally you have to substitute liquid enthalpy values, because state 3 and state 4 are in before saturated liquid region, they are in liquid region. So therefore this is the pump efficiency formula. You must remember, these will be used to solve the problems. Hope you have understood the theory. Now let me discuss one more point, that is the formula. It's a revision of basic thermodynamics. Here this is the saturated liquid line, here you have, this is Hg, this is Hg, and this one is H1. There is a difference, this is Hg1, this is Hg1, this is that is boiler pressure, this is condenser pressure. there is a difference, this difference, enthalpy difference, because on y-axis H1 minus Hg1 will be delta H. So this is delta H. Delta H will be Cp into delta T. This is T superheat 1. This will be T saturation 1. See here on this diagram, this is T superheat, this is T saturation, this is the delta T. So Cp into delta T, delta H is equal to Cp into T superheat minus T saturation 1. So therefore finally that is the superheating, means the quantity of heat supplied during superheating inside this process, during this process. Okay, T saturation to T superheat. So finally I will write H1 is equal to Hg1 plus Cp into delta T. So that is Hg1 plus Cp of superheated steam, we take it standard as 2.1 kilojoule per kg Kelvin to T superheated at 1 minus T saturated 1. Okay. So during superheating process there is again change in entropy also. Entropy also increases. Here just you can look into this. Here at this point entropy is, this is the point, and at this point entropy is, there is a change in entropy. This change in entropy delta S is given by Cp ln of T superheat upon T saturation. So this is the basic thermodynamics formula, please remember that. So both this formula and this formula will be using while solving the problems. Now friends, let us discuss a problem on actual vapor power cycle. Let me read the problem on vapor power cycle, actual vapor power cycle, numerical. Steam enters the turbine of steam power plant operating on Rankine cycle at 10 bar. He has also mentioned temperature 300 degrees Celsius. The condenser pressure is 0.1 bar. Steam leaves the turbine at 90% dry. Means actual condition of the steam coming out of the turbine, he is telling it is having a dryness fraction of 0.9, that is 90% dry. Calculate the adiabatic efficiency of the turbine, eta T he is asking you to calculate, and also the cycle efficiency neglecting the pump work. It is a problem from VTU question paper. So as usual, after understanding the problem statement, so let us write the given data. Given data is P1 equal to 10 bar. Temperature of the steam at state 1 is 300 degrees Celsius he has given. And condenser pressure he has mentioned it as 0.1 bar in the problem statement. And x2 dash, I am not writing it as x2. Actual condition it is. Okay, actual cycle problem it is. So 90% dry. x2 dash, I am writing it as 0.9. So how you decide this is a actual vapor power cycle? Because he has asked you to calculate adiabatic efficiency of the turbine. Means turbine is not having 100% efficiency. Hence this problem belongs to actual vapor power cycle. So x2 dash I am writing. Then what we need to calculate? We need to calculate the efficiency of the turbine and efficiency of this Rankine cycle. So friends, here let us solve this problem. So at P1 bar, P1 equal to 10 bar, at P1 equal to 10 bar, so let us note down the saturation temperature. See here it is available on page number 11. So page number 11 it is available. So at 10 bar pressure, see here at 10 bar pressure, the saturation temperature is 179.9 degrees Celsius. See, saturation temperature I have noted down 179.9 degrees Celsius saturation temperature. See, but steam temperature is given as 300 degrees Celsius. So therefore T1 temperature, that is 300 degrees Celsius, is greater than saturation temperature. If temperature is greater than saturation temperature, the steam must be in superheated condition at state 1. So therefore state 1 on the TS diagram we can mark it in superheated vapor region. So after understanding this, let me write T superheat 1 is equal to 300 degrees Celsius plus 273 is equal to 573 Kelvin. So let's draw the TS diagram considering steam at turbine inlet is in superheated condition. So state 1 I am marking in superheated vapor region. 1 to 2 isentropic expansion, ideal expansion, that is S1 is equal to S2 at entropy remaining constant. For actual process of this 1 to 2 dash I am marking here. So here x2 dash is 0.9 he has mentioned. So 2 to 3, that is condensation process happening at 0.1 bar pressure. So 3 to 4 pumping process. So 4 to 1 this one. Here he has asked you to neglect the pump work. So pump we are nowhere considering. Here for the same problem statement we can also draw the enthalpy entropy diagram. So enthalpy entropy diagram. So this is the vapor dome, saturated vapor line, this is saturated liquid line. So state 1 is marked in superheated vapor region. So this is the 10 bar pressure line, this is condenser pressure 0.1 pressure line. So state 1 to 2, that is isentropic process, S1 is equal to S2 is marked here. 1 to 2 it deviates, 1 to 2 dash it deviates because of losses happening in the turbine. Then 2 dash to 3 it is condensation process, 3 to 4 dash is actual pumping process, 4 to 1. So here if we observe again, this is Hg1, here enthalpy at state 1 is H1 minus Hg1, that is delta H equal to Cp into delta T. So Cp T superheated minus T saturated at 1. So we have discussed this formula. After understanding this one, the next step is we have to note down the properties from the steam table. At 10 bar from page number 11 in the steam table, from page number 11 in the steam table, so we note down for 10 bar pressure line, this is saturation temperature line, this is the HF value, HFG value, Hg, but we take Hg value, that is 2776.2. Then we also take Sg value, this is the Sg 6.583 kilojoule per kg Kelvin. The same values I have noted down here. Now coming to the condenser pressure, that is P2 equal to 0.1 bar. On page number 7 in the steam table we have the properties at 0.1 bar pressure. So this is the 0.1 bar pressure. So this is the VF value, this is the VF value that we can note down. Then again HF is 191.8, so I have written down here 191.8. HFG is 2392.9, I have noted down 23.92. Then again SF is 0.649, I have noted down 0.649. Similarly SFG and SG values I have noted down from the steam table. So after this, noting down the properties, so we need to start with the solution. First let us calculate adiabatic turbine efficiency. Friends, we have already understood turbine efficiency formula. It is nothing but H1 minus H2 dash divided by H1 minus H2, that is H1 minus H2 dash divided by H1 minus H2, that is the turbine efficiency formula. In this formula, if we calculate the values of all these parameters, we will be able to calculate the adiabatic efficiency of the turbine. So H1, let us determine the value of H1, that is enthalpy at state 1. So enthalpy at state 1. State 1 is in superheated condition. So H1 will be what? H1 will be Hg1 plus delta H, that is Hg1 plus Cp into delta T. So I have written the same value. H1 is equal to Hg1 plus enthalpy of superheat. So that is Hg1 plus Cp into T superheat 1 and T saturated 1. So we have the data here. Please note down Cp for steam while superheating process, we assume it as 2.1 kilojoule per kg Kelvin, and T superheat we have already Kelvin converted value 573, T saturation we have the value, so we calculated H1 value. So here it is the unit balance for you. So we calculated H1 in this formula. Now we are supposed to calculate H2 and H2 dash. So let us think about H2 now, that is enthalpy at state 2. So for isentropic process, the process is represented on TS diagram 1 to 2. S1 is equal to S2. So now point 2, he has given that x2 dash as 0.9. x2 dash as 0.9. See here 0.9 in the sense this is x equal to 1 here, x equal to 1 on this line. 0.9 means before this saturated vapor line, means 2 dash actual steam itself is wet. So then 2 is still in the inner side of the wet region. So state 2 must be in the wet region. So therefore state 2 must be in a wet steam. So for wet steam in the wet region, enthalpy formula we know H2 is equal to HF2 plus X2 into HFG2, that we write. So we have the values already that we have noted down from the properties. This is the value, but X2 is unknown. For X2, what is the usual process that we follow? We consider the isentropic process 1 to 2, that is S1 is equal to S2. So S1 is equal to S2 we put, but we can calculate S1 value here. S1 value. So S1 value we don't know. S1 is nothing but Sg1, that is entropy here Sg1 plus change in entropy during this process, superheating process. So that is Sg1 plus change in entropy during superheating process. So Sg1 plus Cp ln of T superheated upon T saturation during the process at boiler pressure. So we have the values 6.583, 2.1 ln 573 by 452.9 T saturation. So these are the values. So after this I calculated S1 value 7.0769 by operating calculator. So which must be equated to S2, that is entropy at point 2. Friends, please note down, if S2 is 7.07, if S2 is 7.07 here, S2 is 7.07. So we have Sg2, that is, what is Sg2? Sg2 is 8.151. Here entropy Sg2 is 8.151, but S2 is 7.07, so which is lesser than Sg. So therefore I am writing it mathematically here, S2 is less than Sg2, 8.151 kilojoule per kg. So hence point 2 is in wet region. So therefore state of the steam at condition 2, that is state 2, is wet steam. So because of that I can write the formula entropy at state 2 is equal to SF2 plus X2 SFG2, X2 plus SFG2. So because of condition S1 equal to S2, S1 we have the value, S2 I substituted that formula So SF2 I am substituting the property from the steam table, X2 I am keeping as it is, SFG2 property from the table. So because of this I am able to calculate dryness fraction at state 2 X2. So now I will substitute this X2 in H2 formula and I calculate H2 as 2240.12 kilojoule per kg. So this is the H2. Now we calculated in turbine efficiency formula H1 and H2. We are remained with H2 dash. So how to get H2 dash? See, 2 dash he has given state 2 dash. We know this is the 2 dash in TS diagram. So state 2 dash is at 2 dash the dryness fraction is 0.9. It is not x equal to 1. So hence 2 dash is also in wet region. So I can write the formula H2 dash is equal to HF2 plus X2 dash into HFG for the wet region. We know the formula. Apply the formula. So therefore H2 dash is equal to HF2 plus X2 dash HFG2. Since steam is at 2 dash is in wet condition. So X2 dash he has given, HF2, HFG2 we have the properties from the steam table, 0.9 he has given. So this is H2 dash. So finally I am able to substitute the values, calculated values in the turbine efficiency formula. I am able to calculate adiabatic efficiency of the turbine as 86.64%. Now he has also asked us to calculate cycle efficiency neglecting the pump work. So we know cycle efficiency net work upon heat supplied, cycle efficiency turbine work minus pump work upon heat supplied. Pump work is 0 because he has told us to neglect. So turbine efficiency, cycle efficiency is turbine work divided by heat supplied, that is Q1. So now turbine work is H1 minus H2 dash I need to consider because it is a actual vapor cycle problem. H1 minus H2 dash divided by H1 minus HF4 it is. So that is heat supplied is H1 minus HF4. So now here let us think about HF4. HF4 is HF3 plus WP. We already know that point HF4 is HF3 plus WP. So that will give you HF4. But WP is 0. He has told us to neglect. Therefore HF4 is equal to HF3. But HF3 is again HF at 0.1 bar. HF3 is HF at 0.3 is HF at 0.1 bar. So that is at 0.1 bar HF is 191.8 kilojoule per kg. That is HF2 that we have already written. So now we are able to substitute the values H1 minus H2 dash, H1 minus HF2. So corresponding values we substitute and we are able to calculate the efficiency of the cycle as 24.07%. Thank you.